The modern educational system relies on a central assumption. If an institution provides a comprehensively licensed, expertly structured syllabus, skill transfer is guaranteed. Traditional methodologists map fixed programs to passive learners, acting as receptacles for information. This model optimizes for standardized compliance. Its roots lie in dogmatic classroom structures, where strict discipline supersedes critical thinking. Modern instructional designers face an entirely different landscape. They must build agile systems, prioritizing the learner's active agency over passive absorption. Modern instructional design focuses on engineering specific conditions a learner needs to transition into practical activities. University 20.35 serves as a live laboratory for this transition toward data-driven environments. University 20.35 runs highly complex educational intensives with zero fixed schedules and absolutely no traditional lectures. This presents a structural mystery. How do seemingly unstructured, schedule-less environments reliably produce rigorous, measurable, high-level technical skills? To build genuine agency, designers must abandon linear syllabus structures. They must engineer agile, data-driven environments that react to the learner's digital footprint in real time. This chart illustrates Yazvin's vector model, a framework used to engineer specific educational environments. The vertical axis measures student activity, and the horizontal axis measures their freedom. The bottom left quadrant represents the dogmatic environment. In this sector, we find strict schedules, the expectation of a single correct answer, and heavy penalties for errors. This conditions learners to remain passive, waiting for top-down instructions before taking action. Moving up the activity axis brings us to the career environment, a common operational trap for modern universities. Here, learners are highly active, but they are completely constrained by predetermined ladders and rating systems. They exert effort, but they exercise no true choice over their trajectory. The target design space is the top right quadrant, the creative educational environment. Operating in this sector requires designers to strip away rigid penalties for failure. The environment forces learners to generate their own educational requests to solve immediate problems. Traditional curriculum design fails in the creative sector because pre-planned schedules remove the learner's mandate to choose. Historically, instructional designers relied on the ADDIE model: analyze, design, develop, implement, and evaluate. The critical flaw of ADDIE in tech-driven education is its architecture. It is a slow, strictly sequential pipeline. Software interfaces and tech industry requirements iterate rapidly. By the time an ADDIE cycle produces a finished 38-hour course, the target platform has already released a new update. This mandates a shift to the Successive Approximation Model, or SAM. SAM relies on extremely short preparatory phases. Designers execute rapid prototyping and move immediately to live testing with users. This creates a modular advantage. Instructional designers can build courses like a constructor set, swapping out micro-modules the exact moment a software platform updates. In dynamic environments, the speed of iterative feedback holds vastly more value than the comprehensive perfection of a finalized syllabus. If you remove standardized testing and fixed schedules, how do you measure learning in a creative environment? You measure the digital footprint. This is the unstructured trail of chat logs, project artifacts, and problem-solving behaviors a learner leaves in their wake. On its own, this unstructured data is useless chaos. It requires a massive, highly specific underlying rubric to map against. This diagram illustrates University 20.35's solution, a 2,000-node taxonomy tree built directly by analyzing 150 million market vacancies. It divides competencies strictly, separating a broad subject skill, like 3D modeling, from an instrumental skill, like navigating the specific interface of SOLIDWORKS. Semantic and ontological analysis, an AI protocol, reads student text chats and automatically maps their language directly to these notes on the taxonomy tree. The strict rule of footprint analysis is the complete avoidance of value judgments. The system generates no standard grades or ABC ratings. True competency tracking abandons testing recall. It operates by continuously capturing and tagging objective evidence of applied logic in the wild. We can observe how this theory functions in practice at the University 20.35 intensive. Student teams receive an industry problem, but no schedule and no pre-assigned lectures. They must organize their workflow using Trello and Discord. When a student's task card stalls in a Trello column, it acts as a bottleneck trigger. The system immediately identifies the exact point of friction. The environment then executes an automated response, instantly recommending a micro-learning module specific to the stalled instrumental skill. Knowledge arrives right at the point of need. A similar framework operates in a high school class called World Creators, which functions entirely as a Discord-based role-playing game. Using a flipped classroom mechanic, students receive complex in-game tasks, like mapping city taverns using coordinate geometry, with zero prior instruction. To succeed, students independently source YouTube tutorials, solve the mathematical problems, and act as informational brokers, teaching their peers. This peer interaction generates a massive, trackable digital footprint of metaskills. In both scenarios, the environment itself becomes the responsive teacher. It reacts to live data to provide just-in-time knowledge, completely replacing just-in-case lectures. This visualization shows the digital profile, the final output of this constant background mapping. It plots precise data peaks across meta, instrumental, and subject skills. This continuously updated profile serves as an empirical map of the learner's true cognitive development and practical capabilities. Compare this to traditional institutional endpoints, which output diplomas that only prove a student complied with a fixed schedule. Instructional designers now operate as ecosystem engineers. They build adaptive environments that monitor digital footprints and adjust educational friction in real time. By designing for the digital footprint rather than the standardized test, we stop optimizing education for passive compliance and start optimizing it for human self-actualization.